Hi everybody, Dan Hewitt here, and you're joining us at Chamber A. It's a historic landmark. It's one of the largest vacuum chambers in the world. I'm joined right now by Mary Saramelli, the lab manager of this facility. Mary, thanks so much for being here today.
No problem,
Yeah.
It's great.
So first off, real quick, give us a little history about this chamber. I mean, it's huge, it's large. What's it been through? What's it here for?
It was built in the early 1960s and mid-1960s to test the Apollo spacecraft that went all the way from low Earth orbit to the moon. So that's why it's so large, because that was a fairly large spacecraft that needed a lot of room to be able to experience the full thermal and vacuum environment of space.
And it's been getting a lot of upgrades lately because
Yes.
What have you guys used the chamber for in the past?
In the past, we've used it for mostly things that were too big to be tested in smaller chambers, such as the large payload bay radiators for space shuttle, or the radiators for space station, the thermal system for space station. Also vehicle-size things like the Beagle lander airbag system that went to Mars. We've also used it for some movie making too. Armageddon, Future World.
So it's definitely a little famous.
Yes, it's our resident diva.
Okay.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Look at that.
They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing. Look at that.
That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this. The reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the earth. So he concluded they weren't.
Okay, this is a simple experiment where you're going to show that we can get a book and a piece of paper to fall at the same rate without the use of a vacuum chamber. Okay, so first let's just go ahead and look at the standard way that they explain this. All right, so we're going to drop the paper and the book, and obviously we know what's going to happen is the book's going to hit first because it's more dense. So go ahead and drop it. Right, okay. So now we're going to pick it up and we're going to change. All right. This is what you have. You got the book and then you got the paper. So we're going to put the paper on the book. All right. And then we're just going to drop the book and let's watch what happens. It's a miracle. The book and the paper fell at the same rate. Why? Because the book was pushing the density, in this case is a gas, which is air, to the side, allowing it to be in a vacuous state. So you do not need a vacuum to attain this, and this is part of the whole deception of gravity.